So the conventional automotive steels which were actually used in a couple of decades earlier, which were already they were getting replaced with the advanced high-strength steels, which we are looking at the last unit. So now we will look at some of the introduction, basic introduction about these conventional steels, and we were looking at, say for example, the IF steels, the IFHS, the mild steel, the Baconic steel, and common manganese, HSLA, and ferritic magnetic steels. And if you recall my previous lecture, the majority of the conventional steels, if you look at it, they were all low carbon steels, which have excellent ductility. If you look at it, for example, IF steel, the percentage of elongation is about say 40 to 50%. And these steels, they were easy to produce, as well as because of the high elongation, uniform elongation with very low stress to yield. These steels were conventionally used in automotive industries in a large amount. If you look at the actual the microstructure, they are very simple, either ferritic microstructures or ferritic pelletic microstructures. Say for example, IF steel is known as interstitial free steel. See, these steels they possess excellent ductility, so about 40 to 50% ductility. So this is actually coming from the fact that the carbon concentration of these steels is extremely low. Within few ppm carbon concentration we had. The carbon atoms which are added in iron matrix, generally they occupy the interstitial positions in between the iron atoms. But we add another some special alloying elements to pin the carbon atoms from interstitial positions by adding say for example vanadium or niobium or titanium to the steels, and these elements which are added, vanadium, niobium, titanium, and few ppm amount, and these vanadium, niobium, titanium, they combine with the carbon atoms and form carbides of vanadium, niobium, titanium. So by forming carbides, we deplete the iron matrix free of interstitial atoms. So the carbon actually is taken out from the interstitial positions by these elements to form vanadium carbide, niobium carbide, titanium carbide. Because of this carbide formation, we are now having a pure ferrite matrix. So because of the pure ferritic microstructures, these steel have excellent ductility. If you look at it in this banana diagram, the IF steel has the maximum uniform elongation, about 40 to 50%. So this steel, it's very attractive in early say late 90s when the automotive industries, they were trying to get steels that can be easily formed during while making components for auto bodies. So the IF steels, it's been used even now in some of the automotives for low load bearing members, for example roof or door panels, because we can easily form this steel. So again, I mean the trend went on to identify the high strength steels. So these automakers, they wanted to increase the strength of the steel, as I has been explaining in earlier slides. So they started using somewhat higher amount of alloying elements such as vanadium, niobium, titanium to form more carbides in the steel, so that the strength can be increased slightly higher than the conventional IF steels. So the IF high strength, the interstitial free high strength steel, they possess slightly higher amount of micro alloying additions of niobium, vanadium, titanium to have precipitates volume fraction increase in the microstructure, thereby providing precipitation hardened. So from IF steel, the IF high strength steels were developed by adding a slightly higher amount of vanadium, niobium, and titanium, and the strength increased from say 200 to about 300 megapascal and thereabout. So by increasing strength, obviously the ductility elongation decreased slightly, but still the IFHS is considered better than an IF because we gain a lot of strength improvement, and still the ductility is 40 to 40%, so which is reasonable to use these steels in place of the conventional interstitial free steels. And the other type of the conventional steel which were commonly used in automotive application is a simple ferritic pyrrolitic mild steels. So these steels were very simple alloying additions and also very easy to produce with simple heat treatments because the microstructure is not that complex. So the mild steels. So these were all classified into deep drawn deep drawn and extra deep drawn grades, DDD and EDD grades, containing the ferrite and then pearlite microstructures. The pearlite volume fractions again dictated by the carbon concentration, as already explained in the phase diagram. Based on the carbon concentration, you may form some amount of productide ferrite, and remaining would be pearlite. So these grades they are also providing excellent elongation as well as reasonable strength comparable to IF steel, strength varying from 200 to 250 MPa. And these steels were also attractive of automotive applications because of the excellent ductility they offer, because of the excellent ductility and uniform elongation, and we can draw it and we can stretch it and we can make components from the deep drawn and the extra deep drawn grades. So the other conventional steel before the development of advanced Asian steels, one of the steels is the Baker Harding steels, BH. So this steel also contains very low carbon concentrations, in a few tens of ppms, the parts per million. And unlike the IF steel, the Baker Harding steel does not have microalloying additions. So we deliberately leave carbon in interstitial positions. Okay, so carbon is actually present in the interstitial position for one very important reason. Again, this steel contains very low carbon, and the carbon atoms are kept in the interstitial positions. So why do we keep that? In IF steels we take it out and form microalloying precipitates, whereas in Baker Harding steel we keep the carbon atoms in the interstitial positions. And why do we keep it? Because these steels, when you deform it, okay, so you anneal, and subsequently when you bake it in a paint baking cycle, okay, so you make a component, you deform it, whatever deep drawing or stretching, and then you send the component after painting to baking cycle. So we all know that the increasing in strength by the interstitial atoms, by the interstitial carbon atoms, when you have a driving force, the carbon atoms go and segregate to dislocation fronts. Okay. So these carbon atoms, when they migrate during the slightly increasing temperature provided by the paint baking cycle, the carbon atoms they go and decorate the dislocations, and thereby hindering the motion of dislocations in subsequent forming. So in the Baker Harding steel we leave the carbon atoms deliberately in interstitial positions. So these carbon atoms can migrate and then go and occupy the dislocation fronts and forming a coronal atmosphere. And this happens, this migration of carbon atoms to the dislocation front happens during paint baking cycles, because you need some driving force for carbon atoms to migrate and occupy the dislocation fronts. So you have an interstitial carbon begin with, and you make component out of it, and after you make the component by forming, you apply paint and then components sent for paint baking cycle, and during this paint baking cycle the carbon atoms migrate to the dislocation front, and once the carbon atoms decorate the dislocation front, subsequent deformation become difficult because the deformation is driven by the mobility of dislocations. Then material gains some strength because you are providing new barrier for dislocation motion. So you can form it, the material still have reasonable ductility, about 30% elongation, and you form the component, but after forming and during paint baking cycle, because of the migration of carbon atoms to dislocation fronts, components gains slightly higher strength than without paint baking. So the strength regaining can go up to say about 30 to 60 MPa, which is considered at that time very good, because the base material have materials containing the strength of 250 MPa. After paint baking cycle, you gain about 30 to 60 MPa strength. So it is useful, especially because all the automotive components are also painted and then baked. So we take the advantage of the carbon migration dislocation front to increase the strength and subsequently. So these steels like in IFHS and Bacon steels and mild steels, they were all considered now the conventional steels because they are very simple and they provide very good formability. So the automakers found it very useful because they can form the components with easy mill loads, because of high elongations. These materials can also be made into various components in automotive parts. But as I earlier explained, because of the increased norms of the fuel efficiency as well as safety performance, the automakers, they found that these steels cannot meet the emission standards that were actually coming up over the years. In order to meet those standards, as I already explained, the auto parts should be made into lighter and stronger. So again, if you want to make the auto parts lighter and stronger, we'll have to go for high strength steels, right? So the options which were available for automakers in late 90s for the steels which are actually with an increased amount of alloying elements, for example carbon manganese and chromium and silicon added steels, and high strength low alloyed steels, to some extent ferritic binetic steels. Okay, so these are all again the simple microstructure ferritic pelletic containing steels with slightly higher amount of manganese chromium, which can provide the substitutional solid solution strengthening. And because of these strengthenings of alloying elements, the strength increase to higher levels than the conventional the IFHS and BS steels. And because of the simple microstructures of ferritic pelletic or ferritic binetic, the ductility decreased significantly. So for example, in a simple carbon manganese ferritic pelletic steels, the strength level went up to 500 to 600 MPa, but with drop in elongation compared to the IF steels. So the formability became a big issue for these steels. If you want to make deep drawn components or components requiring an extensive deformation while during processing, these steels they did not give enough ductility during forming operations. So people wanted to invent new microstructures which can provide both strength and ductility. So the automakers demanded the steels should possess a significant ductility, not as compared to as good as the IF steel, but reasonable ductility. But the strength levels would also be increased so that these steels, the conventional steels, IFHS, BH, can be replaced with even mild steels can be replaced with high strength steels. but by doing so these steels should also be able to formed into various parts. So the driving force now for developing the advanced sites in steels is actually coming from the fact that the high strength ferritic palladic steels do not have enough ductility, and with the given strength of HSLA we won't gain any advantage in terms of manufacturability because of reduced elongation ductility. So yeah, then a lot of research went into develop new microstructures with an objective of developing steels which actually lies diagonally to this graph. So we need to have reasonable strength as well as acceptable ductility. Okay. So in order to do that, as I already explained, the conventional ferritic palladic microstructure cannot meet both the acceptable ductility and strength combinations. So the steel makers they were already using various microstructure combinations to obtain the strength and ductility which is required to make the automotive components. The first development happened in this line is to develop microstructures containing two phases, dual phase steel. So where the dual phase here denotes the ferrite and martensitic microstructures. Okay. So we form a microstructure containing a ferrite and martensite. As already explained, the martensite actually forms from the austenite when you rapidly cool to room temperature and by a diffusionless manner or displacive manner. And the martensite also provides a very high strength compared to the ferrite. And during this process of martensite formation, and there is also considerable increasing volume in terms of the expanding the crystal structure when the FCC transformed to body center tetragonal. And we can make use of the advantage of the properties of martensite in terms of mechanical properties and the volume expansion that actually happens when the martensite forms in austenite or surrounding ferrite matrix. And in subsequent slides we will see what advantage this microstructure is going to bring. But as of now, you can understand that the DP steels, dual phase steels, can have the ductility ranging from say 30%, and the strength can be increased up to the 1200 to 1400 MPa. So range of properties can be obtained by changing the morphology and the volume fraction of ferrite and martensite mixture. And we will see in detail the actual the formation mechanism and why dual phase steel can give you the elongation as good as the Baconic steels and strength which can go more than 1 gigapascal. Okay. And this became very attractive because now we have a material with very high strength and acceptable ductility, and we can reduce the now thickness of the conventional steels to achieve the light weighting. And by increasing strength, we are not reducing the ease of forming or formability, because dual phase steel can also give very good formability. And apart from dual phase steels, there are two other steels which require a complex microstructure to achieve the strength and ductility combinations. The ones actually is strip steel. So what is strip steel? Trip here stands for transformation induced plasticity steel. Transformation induced plasticity steels. I will come back to the explanation of what is transformation induced plasticity in subsequent slides. So right now you can understand that the trip steel has a multi-phase microstructure containing ferrite, bainite, so we can say bainite, and some amount of retained austenite. Okay. And yeah, because of this special multi-phase microstructure, and trip steel again has excellent ductility as well as good amount of strength. So in order to obtain such a multi-phase microstructure, and we also need to have special heat treatments and alloying elements, but because of this multi-phase microstructure, especially the presence of retained austenite, we can achieve reasonable ductility and strength. So the another steel in this class, this complex phase. The complex phase steel is similar to dual phase steels, and these three steels and DP, complex phase and trip steel, they actually fall in first generation advanced silicon steels. Because these steels, they were the first one to be commercialized, and some amount of trip steel and dual phase steels very widely used nowadays in automobile bodies, and the strength level varied from close to 500 to 1000 MPa. So these steels, they started coming to commercial applications in early 2000 or so. And they provided much needed lightweighting possibilities because of the increasing strength the steel possesses, as well as the ductility which is needed to form the components of the auto parts. And if you look at apart from these three the steels, this diagram also shows various the next generation steels. For example, the first and second generation is mainly trip, DP and CP with strength up to 1000 MPa, and we are actually moving from the first and second generation to achieve a diagonal growth. So for example, the steels with modified DP, dual phase steels. So we also have various quench and partitioning steels, as well as TWIP steel. And TWIP steel, it is still not commercially used, but this gives a great potential for weight saving applications, but there are some limitations in terms of alloying elements. So we are not going to really look at, because it's not really commercially applicable. TWIP stands for twin induced plasticity steels. And apart from the steels which possess a very good strength and ductility, so you also have one generation of steel which is now becoming very interesting for commercial application, is boron containing hot forming steels. Again, the hot forming steels, if you look at the compositions, HF stands for hot forming steels. In hot forming steels, the composition is similar to ferritic paletic, the carbon manganese steels what you see over here, but the forming mechanism, the how you make parts out of these steel is different, and slightly adding the small amount of boron, and we can increase the hardenability significantly. So you form the steels at high temperatures, and subsequently you cool it to room temperature. During cooling process, the entire microstructure becomes martensitic. So you begin with a ferritic paletic microstructure, you take it to austenitizing temperature and deform it at austenitizing temperature, and then subsequently cool to room temperature. And during this cooling process, after you make the components microstructure becomes completely martensitic. Thereby the strength of the component is increased to close to 1500 MPa ETS. So we will see in detail in subsequent slides the actual physical metallurgy of dual phase steels and trip steels and hot forming steels, and how we can achieve that these excellent combination of microstructures which can give both strength and ductility, as well as how we can achieve fully martensitic microstructure from ferritic paletic microstructure upon forming. Okay. Apart from that, if you look at it, these grades, some of the steels like fully austenitic and annealed steels, these are very expensive in terms of alloying elements, because in order to form complete austenitic microstructure, you may need to have to add nickel and chromium. So so we are not going to really look at in detail the austenitic stainless steels. And again, as I explained, TWIP steels, now they are in under development. These steels also contains a high amount of manganese in order to form a twinned microstructure, and the weldability of this steel is still considered very poor if you use the conventional welding processes. So we will also not be looking at these two steels. So we will look at in subsequent classes the physical metallurgy of these first and second generation advanced ASN steels, and the hot forming and complete martensitic steels which have very high strength upon forming. So in order to summarize this graph, the automakers and the steel makers, they are going for diagonal growth of steel development, where steel contains both high strength as well as acceptable ductility. Because of the light weighting, the conventional steels are all getting replaced with these advanced ASN steels in order to achieve better mileage as well as the cross performance driven by the increasing strength. Okay. So this graph shows the use of advanced ASN steels and ultra high strength steels. Again, ultra high strength steels nothing but steel generally contains UTS of more than 1 gigapascal. This is the trend of usage of advanced ASN steels in auto bodies. So this is in y-axis we see net pounds per vehicle, and over the years, if you look at in 2012, the total amount of weight of steel that is actually advanced ASN steel used about 205, but it is actually continuously increasing. So now it's already about 330 pounds, and it is expected to go close to 480 pounds by 2025 in order to meet the emission norms, which I already showed in my previous slides. For example, if you want to meet Euro Bharat 6 norms, and we'll have to reduce the weight of the car significantly. So as I explained, unless the conventional mild steels are replaced with lightweight steels or any other alloys, we cannot achieve the emission norms. So therefore, more and more advanced usage of advanced ASN steel is foreseen over the years. So this is the forecast right now what we are in. So for compared to 2012, and it's going to go up because of the stringent emission norms is going to come over the years. And this slide actually shows again the comparison between the various materials used in auto bodies. So comparing 2007 and 2015, if you look at it, as I explained, the ferritic paletic steels, the mild steels, they occupied the majority of auto bodies, about 55%, as I showed. Compared to 2017, if you look at 2015, the majority of mild steels are all replaced with advanced ASN steels, mainly dual phase and trip or complex phase microstructures. And as well as the conventional ASN steels, which are carbon manganese or ferritic magnetic steels in some applications. So you already see over 7 years or so in last decades, the majority of mild steels are all replaced with advanced ASN steels. The use of mild steel is significantly reduced, and you still have for low load bearing structures, Bake-Honorable and the interstitial free IF steels, interstitial free high strength steels. And if you see the trend now is the use of advanced ASN steels keep on increasing. The main beneficiary in terms of weight saving is the mild steel. The mild steels are all getting replaced with an advanced ASN steels. So, we will go in detail about the mechanical properties and microstructure of these steels. So, why again the strip and DP steels of first generation, they were very attractive in terms of mechanical properties is shown in this slide. So, this is a simple tensile testing result of HSLA and trip and DP steels. So, HSLA is high strength low alloy steels. So, if you look at steels, all these three, trip, DP and HSLA, the yield strength is similar, right. But if you look at the actual graph, for a given yield strength, all these three possess the yield strength of 350 megapascal. But if you look at the curve of HSLA, trip and DP, even though all these three steel have equivalent yield stress, the ultimate tensile strength of DP and trip is much higher than the HSLA steels. Apart from the increasing the ultimate tensile strength, and the trip and DP also gives excellent uniform elongation. Okay, you see that the elongation percentage increased significantly, as well as the other important point over here, in the HSLA steel they show yield point phenomena, right. So, this is considered not acceptable or it is not considered beneficial, especially if the material is formed deep drawn or stretched to make auto components, because you will end up forming what you call a lotus band. So, lotus band formation significantly affect the surface appearance of the components that are stretched or that are formed. So, apart from the advantage of increased uniform elongation, the DP and trip steel, they also give deformation without the yield point phenomena. Okay. So, the advantage in terms of increasing strength in UTS, ultimate tensile strength, as well as the total uniform elongation, which is increased significantly. The DP and trips were considered very attractive to replace the conventional high strength and conventional ferritic pelletic steels. Okay, so we like to summarize here. So, we looked at the various modern advanced size and steels, how these steels were found to be attractive compared to the conventionally used ferritic pelletic or simple pure ferritic based steels. And we also looked at the steels that are getting developed, for example trip steel or austenitic stainless steels, and why we need to have a diagonal growth in elongation and in terms of elongation as well as the strength in the material. And we also looked at the trend in the usage of commercial applications of usage and commercial application of advanced size and steels over the years. So, it is going to go increase because to meet the emission norms. So, the conventionally used mild steels are all replaced with the advanced size and steels. So, about 55% of mild steels which were used in late 90s are all replaced with advanced size and steels, and yeah, we are going to go even further. And the properties of trip and DP steels, they are superior to the HSLA steel in terms of uniform elongation as well as the increasing yield stress, the ultimate tensile stress for a given yield stress. And apart from the strength and the elongation advantage, and DP and trip steel, they also do not show yield point phenomena. So, the surface appearance of the components that are formed, they are also better than the HSLA steels.